Okay, cool. I promise I'll be quick. Drinks are going to be soon. So my project was testing counterfactual mechanisms. If you have no idea what that means, I actually looked it up for you. So in terms of the project, we can think about something that did not happen and how to relate that. That's like the counterfactual in here. So this the area is fraud detection, which I was lucky to get a project in. I love this area, and this relates to the retrains of a predictive model for fraud, and I'll show you exactly how. So if we are doing some retrainings, what data do we get? For the retrain and not the original model, you will get data that's actually scored by your production model at some point. And that has a problem with it, because your scored data will have rejected payments, and you know those are actually not released. So turns out you will never get a true label on a rejected payment. You don't know if your rejection was valid or not. This was a surprising thing to me actually, because how this domain is set up is not exactly the same as what we have at Morgan. So think about it like this. You have a card issuer, you have a merchant, you have a user. If you let a payment through and it's a fraudulent payment, then the user would complain to the card issuer. It will occur a chargeback to the merchant, and that's how the merchant knows that this was fraud. Our model runs on the merchant side, so quite obviously, if we stop the payment here, we never reach our source of labels. So that's like the problem. How do we guard against this? Well, sorry, one more thought. So what do we do with these? There are two approaches. So we can either say that, well, this was rejected. I don't care about this payment anymore for the retrain. Well, obviously, we would lose potentially valuable data. We could also say that, well, we thought it was fraud. Let's assume a positive fraud label and use that in the retrain. Well, that's not good either, right? Because you would just reinforce the previous model's bias. Yeah, which sucks. So, and in practice, we tend to exclude. How much time? Wow, perfect. So, this is where we introduce something that we call a counterfactual mechanism. And this thing can tamper basically with your actual model, how you make predictions, and we also tamper with your training thing. So it would do things to that. What it does too is on the next slide. And hopefully this leads to better performance. What do we do? And actually this is, project goals. So I think the most important goal was to create a framework for the company to evaluate these counterfactual mechanisms so they can improve their own model. I also had to implement some basic mechanisms, and since I did not have access to feature spaces actual model, I had to write a baseline one, which is horrible model I came up with, but that was not the point of the project, so I think it's fine. I used Python 3 for the language. I actually ended up creating two separate versions of the same thing. One the classic way, NumPy, Pandas, sklearn, we all love it, and also a distributed PySpark-based version for bigger data sets. And for the quite simplistic model, I used LightGBM. I should charge money. I should start charging money from Microsoft for advertising their products, but it's really awesome. And I just like to highlight that all of the stuff is unit tested, so I hope they will use it. This is, I'll probably just skip mostly. The gist of it, there's a simulator, you plug data in, use some selection strategy, and you put the counterfactual mechanism in, it runs a simulation, you get some results. Let's just skip. Yeah, how do we do what we do? The most basic solution is to just release some of the payments that we actually think are fraud, and maybe we can say that we would let 5% of the payments through. So what this shows is like the probability of releasing a payment based on what the model actually classifies it as. So there's like a breaking point at like half, right? Below that, we release a payment, it's not fraud, and up from there, we release it with a 5% probability. This will actually give us some information back for the 5%. Just bear in mind this has a cost, right? Chargeback has a cost, fraud has a cost, so you might want to have like a budget of doing this and see what to do. When we got the actual labels, we would weight these payments a bit more to fight against the fact that we only let a few of them through. So this is nice and actually works quite well. You'll see in a second. There's a problem with it that you can argue we could do better because the probabilities are constant, right? And the probability of the stuff being fraud is not constant. So stuff here is most likely fraud. Stuff here can go either way, right? So ideally you'd want like more information from this area and not this one. And this is what you can also implement as well. You can create a function like this. We call this propensity function, which basically maps the prediction of the model to the probability of letting the payment through. And if you calibrate your function, you can define how much of these payments want to let through. So get more information from the gray area and just let only a few payments through from the quite obvious area. And the question mark is here because, well, depends if it's better or not. This has to be calibrated. Some results. It really it behaves like you would expect, and also not. Where it behaves like you'd expect is that this is like a recall values for each of these retraining epochs, and red line is essentially the run without any defenses, and the green line is what the ideal case would be if you have like a magic insight and know all of the labels. As you would expect, the two mechanisms push the quality up a little bit to the middle ground between the two. Hope that makes sense. What's really interesting is that on this data set and this model, with this propensity function, what I have found is that the propensity function way is actually worse most of the time than the naive version, and only outperformed the model and two epochs. Yep, F-score values are really, really similar. I would just probably skip this. And I'm still on time. In summary, I've successfully shown that these mechanisms can actually reduce this performance degradation. I implemented this modular framework in Python, both for local and distributed usage. And I had to use an example model, but I also implemented two mechanisms, but I don't think that's really the point. I think the key takeaway here is that my client feature space has a framework now that they can use to experiment with these techniques, put their own model in, and provide better value for the clients when they are done. I also learned a lot about fraud in areas which is not the same that I exposed to in my regular work. I learned about interesting, cool ideas from the real world, how to do this, and lots of technical things around the DB called ClickHouse and PySpark and unit testing PySpark code, which was awesome because I mostly used Spark from Scala before. So.
Can you write a blog post about unit testing PySpark code?
Yeah, sure. Further work, I think the most crucial would be to plug in the feature space model, because that's what they really want to improve, not my dummy, stupid little thing. And once they do that, they can fine-tune the actual mechanisms to maximize the value add. I think that's the most important takeaway. There's actually a presentation about this approach, some slides, which are very similar to these, but you're welcome to take a look. And there's an original paper around counterfactual estimations on a different domain for search engines based from Facebook and Microsoft. That was a really interesting paper as well. So if you like this, you can dive deep in. Yep, thank you for my sponsors who sadly could not be here, but I hear they were happy. And obviously for the Cambridge Spark team for making the whole thing happen, and then you guys for making my last 6 months really awesome. So,